In this video we will deal with Kirchhoffs Law, again in the section of radiation. We'll do a virtual experiment and you will learn there the relationship between absorptivity and emissivity, and then in the course of the video we will answer the question if what we have learned is wavelength specific, if this can be extrapolated to being generally valid without any wavelength constraint. Now let's move on here. We do a virtual experiment. It consists here of a cavity which I call object 1 at temperature T1, and a second cavity where radiation from 1 goes to 2 as temperature T2. Let me take the laser pointer. Temperature T2 is smaller than temperature T1, so there's a radiation flow, intensity flow from 1 to 2. The constraint that we put here is that there is no back reflection through that opening. So whatever is going from 1 to 2 remains there. So what happens is basically that we have so many internal reflections that it's at the end completely absorbed within body 1. This means for long enough times, if you wait until infinity, we will have then T1 equals T2, and the two heat fluxes, the one going from 1 to 2 equals the heat flux that comes from 2 and reaches 1. Now if we have complete absorption, you may guess already that then we can replace that cavity by a black body, or in other words, the radiation of a cavity corresponds to that of a black body. Now let's move forward with that and use the cavity now as an enclosure. I'll put here an object into that cavity. I know the radiation coming from the cavity is black body radiation. That's why there's the index B. And now let's have a look. What is coming to the body and being absorbed? Body has the index 1. That's alpha 1. Of course, depending on wavelengths, time that wavelength specific black body radiation of that cavity. And at the same time, that body, due to its own temperature, is emitting radiation. Now, if we do an energy balance indicated here by this dotted line, what is changing the inner energy is what's coming in and what's going out. So that's shown here. We have the incoming amount of radiation, that's alpha 1 times the heat flux from the black body times the area of the body or the object. And the outgoing one is that emission heat flux times the area. I can now skip here the area and derive alpha is q dot lambda epsilon divided by q dot lambda black body. Now if I look at the emissivity definition that we got to know in the last video, epsilon is heat flux emitted by an object divided by the heat flux emitted by a black body of the same temperature than the object. If I put that in a formula, that's epsilon of lambda is q dot lambda epsilon divided by q dot lambda b. Exactly the same than what is written here. So we have by this derived Kirchhoffs law. The absorptivity at a given wavelength equals the emissivity at the same wavelength. Now this is still cumbersome to deal with because of this wavelength dependency. So we will then go later on and check if we can get rid of that. Before, I'd like to strive a very frequently asked question. And the question is, if I know that alpha of lambda equals epsilon of lambda, are then the absorbed and the emitted heat flux not identical? And the answer is no. Let me show you an example. Here's radiation heat flux of wavelengths shown, 2 Planck curves for example, and the red one has a higher temperature than the blue one. So at that specific wavelength, this is the amount of radiation that's emitted by the red one, and these two are in exchange, and the blue one is showing this here. I will explain that in a minute. So we know the black body with T red and the black body with T blue are in radiative exchange with each other. At the beginning, T red is larger than T blue. Now let's have a video showing what's going to happen. So we have here put the starting point, and we will now show how the temperature of these two bodies evolves over time, and we see here corresponding Planck curves. And what we see is that the red object decreases its temperature in time, whereas the blue one increases its temperature. And the question is, how is it going to happen? Well, the answer is shown here. I use the same diagram, so at this specific wavelength, due to this Planck curve, the red black body emits radiation according to what's marked with 1. That's the heat flux that's being emitted. The blue black body, due to its nature as black body, absorbs all incoming radiation, exactly that heat flux. However, at this wavelength, the blue black body can only get rid of heat flux that corresponds to 2. That's the maximum that this body or object can emit at that wavelength. Now we see we have a difference here between 1 and 2. Let me just go in here. So there is this delta, and this difference is positive for the blue black body. So the blue black body increases its temperature as this difference is positive, and the red body gives more away than it receives from the blue one, so there the temperature decreases over time, and that was shown in the video. So to answer now that question, sorry, I need to get this away here. To answer this question, the absorptivity and emissivity indicate proportions that do not necessarily refer to the exact same alphanumerical value. So the heat fluxes can differ from each other, although the values for alpha and epsilon are identical as a function of lambda. Now let's get to the generalization of Kirchhoffs law. Here's again this cavity with the object, and take the laser pointer, and when I just, as I proved, alpha of lambda is epsilon from lambda. Question is it throughout also without wavelength constriction? Well, let's do a verification. I'll write down alpha average. We saw that last time, that's this integral, and epsilon average, that's the ratio of these two integrals. And if we now make alpha equal to epsilon, we have to make these two equations equal. And is this the case? Well, we'll see that there are two specific cases where this becomes true. The first one is if the object or the body is gray, then its values for alpha and epsilon do not depend on wavelengths. However, still the question remains, are then those in this case also identical to each other, as we have proven it for wavelength specific properties? Let's have a look. We say alpha equal epsilon by this longer equation. We have here the alpha, here the epsilon, and as those are not a function of wavelengths, I can pull both in front of the integral, and if I do so, you see that the ratio of the integral becomes 1 on either side, and at the end I get alpha equals epsilon. And the answer then is yes. If I have a gray body or a gray object, then I can generalize Kirchhoffs law to no wavelength specific properties. The second case is a very specific case. If the emitter is gray or black, means my radiation source, and the temperature of the emitter equals the temperature of the object. This means T source equals Tk, which is marked in red here, and epsilon of the source is not a function of the wavelengths. Well, I want to prove that alpha equals epsilon. Long equation again. So what's absorbed is what's coming on here. That's q dot lambda of the source, and putting this in here, and this is here a little bit more elaborated. What's coming from the source is epsilon times the black body radiation at source temperature, and if I put that in here, I get here the epsilon, black body radiation at source temperature, and here down the same thing. And now I have assumed that T source equals Tk. We will get to that in a second. We can first eliminate epsilon source, because epsilon source was not a function of wavelength, so we could put it in front of the integral or just then eliminate that. Now, with the temperatures being the same as shown up here, the black body radiation at temperature T source is exactly the same black body radiation at temperature Tk, and this means then I have the same standing on the left hand side of the equality sign and standing on the right hand side. So we just take here so this here leads to that, and at the very end I get alpha equals epsilon. However, it's worth to note that this case where T source equals the object temperature, I have no radiation exchange if the temperatures are the same. So yes, I get there alpha equals epsilon, but it's a trivial case, doesn't play any role. So where you should pay attention to is this here. For the gray case, I get alpha equals epsilon. With that, I'm concluding this talk, and the questions that you should be able to answer are, in which case can it be assumed that both alpha of lambda and epsilon of lambda lead to alpha equals epsilon? Then you should be able to tell what part of the radiation is characterized by the emissivity and what is characterized by absorptivity. And also from the video, you should now remember that when alpha equals epsilon, both wavelengths dependent, are then the heat fluxes being absorbed or emitted identical. Thanks for listening.